Afternoon, ladies and gentlemen. I hope everybody is fresh now. If you are not fresh, all the famous speakers will make you really fresh. This late afternoon, in the last session of International Conference of Metal Forming, or Materials Forming, we have three distinguished speakers. The first one is Professor Taylan Altan. I heard his name when I was a child, 30 years ago.
Thank you, thank you.
Again, one of the famous professors and brilliant scientist, Professor J.J. Jonas, mentioned on Taylan Bey. And he told me that Taylan Bey spelled my last name or pronounced my last name not correct.
Not correctly?
Not correctly.
I'm sorry. My apologies, after 30 years.
30 years? Actually, I am very much happy to meet him last evening. And I will be delighted, I am sure, and you will be delighted by listening to his lecture. He is going to talk us today metal forming research for industrial applications. How can we improve industry-university cooperation?
Thank you. Thank you, Mr. Chairman. My first job is to wake you up. In the afternoon, everybody's sleepy, everybody's tired, and I would like to discuss some controversial issues, okay? So, my colleagues from abroad, they already know me, so they don't care what I say. They don't listen anyway. So, my comments are mostly for you, okay? Now, first, I made myself some notes here. You will see two websites. And I suggest that if you're interested, the first website, ercnsm.org, is for the center where we work with industry on one-to-one basis. I do a lot of contract research. I charge people for service, and they have to pay. I write them a proposal. If they are happy, they sign, and they pay. If they're not happy, they don't pay, but usually they pay. The web page that we have is very interesting. The first one, ERCNSM. I suggest, Erman, that you guys here also have a nice website for your metal forming, because in this day and age, web page is very important. One more thing I should mention before I forget. I also publish every issue, now it is once every 2 months, in a trade journal called Stamping Journal. If anybody gets Stamping Journal, I don't know whether from the United States. When you, as a professor, you publish in Stamping Journals, you don't get any credit, because the universities don't count that as, it's not in the citation index, okay? But industry doesn't read those peer-reviewed journals. I am very much against these peer-reviewed journals and this indexing and rating and all that jazz, because it distorts, it makes scientists out of engineers. That means we do hobby research. I call that hobby research. Something we like instead of something which is needed. So, but industry reads relatively simple journals, not peer-reviewed journals. Now, the other Center for Precision Forming is what we use for a consortium. We discussed it, I guess, in Turkey. That is not practical at the moment, maybe in the future. One thing is very, very important for a university to work with industry is trust. Trust. I studied in Germany, did my PhD in the United States, in Berkeley. I worked 2 years in DuPont. I worked 19 years in a research organization in Patel, and I came then in 1985 to the university. And when I came to the university and I started talking to the industries, I wanted to hide I was from the industry in the university. Because as soon as the industry heard I am from university, they started rolling their eyes. They said, well, this guy is going to tell us more stories. Can he really deliver what he says? So trust is extremely important in research, because I keep telling my students, we are not selling cars. You cannot kick tires. You are telling somebody, I'm going to do the best, I'm going to do the best I can, that's what I'm going to do, trust me, I will deliver. And if you lose that trust once or twice, then you're lost. Then the industry is not going to talk to you anymore. Now, I believe one of the most important things we should do is from both sides. We have to understand each other's objectives. And we have to discuss these things very frankly, very openly. Not politely, but frankly. Sometimes we are so polite, we don't tell the truth to each other. We are trying to be nice to each other. But at the end, nothing comes out. We got to be straight. The objectives of the university. The primary objective of university faculty, with some exceptions, is to publish papers, to get promotions, gain recognition among their colleagues. There are a few people who are crazy or nuts like me, who want to work with the industry, and they don't care about publications, but I have tenure, so I don't care. If you're a young professor, an assistant professor, and you want to be a docent, I guess that's what it is in Turkey, so your boss is going to say, how many papers did you publish? You're not going to say how many industry you helped, how many companies you work with, how many papers you published in so-called peer-reviewed journals. So, the goals of the university faculty means professors, is different. The goals of the objectives of the industry is, I got a problem. Usually it's a short-term problem, it may be a medium-term problem. I want you to solve it. And I want you to give me a reliable answer. And I'm not here to give money to you as an industry from my profit so that you can have fun, travel, or write papers for peer-reviewed journals, or train your students. That's not my job. So, I would like to improve the technology. Okay, you can read it. I want to reduce cost, reduce lead times, improve my quality and so on, but I want to solve my problems. So, I believe the first thing we need is we have to understand each other. And we have to understand each other's objectives, and knowing these objectives, we have to see how we can find common ground. How? Just like we do in business. Two companies work together if their interests mutually beneficial, if they can help each other, if they both side profits. The same thing here. If I as a professor, I don't benefit from what you do for me as an industry, I don't want to work with you. If as an industry, you don't benefit from what I'm doing, you don't want to work with me. That's very simple. We are still friends, we can go to have a beer, but we may not work together. So, it's very important that we have communication. Now, what I would like to do, instead of talking a lot in abstract, I would like to give you some case studies how we work with industry. Now, that may or may not be applicable in Turkey. That's a different ballgame. But I give you some examples. By the way, very often what I see is university people like to work on things they like, and they come up with solutions. After they have a solution, they look for a problem. I think it's much better if you look at a problem and then try to find a solution. And believe me, there are many, many, many problems in the industry. So I suggest young faculty members should visit companies, should learn, talk to industry, learn what their problems are, and see how they can bring these problems to their faculty groups. Give you an idea, my group is not very large compared to Professor Tekkayas's group, for example, or other institutes in Germany. It's a very small group, and I have a lot of international students and a number of visiting scholars from right now, a couple of from Turkey, from China, from Germany, and I should add also, I love to have German students. And they come to do a diploma right, which is a master thesis. They are on the ball. They know how to work independently, and they are solid, and there's a reason for it. because the German education system, in my perception, in engineering, is superior to the American and Anglo-Saxon education system. It is based on project, and it is based on more mature attitude, so it is pretty good. By the way, I didn't put it in here, we have software, deform, handstand, LS-Dyna, and so on. So, let me give you a couple of case studies, and we run out of time and I stop. One topic which is very large, important for us, and that may be interesting for forging companies among yourselves. We work with Eaton Corporation on forging of engine valves. You may know Eaton is a worldwide corporation. They make engine valves just for everybody, and also gears for trucks, because they make a lot of truck transmissions. And you can read, I'm not going to read this thing, objectives. Obviously we are trying to reduce die life, we are trying to improve quality, trying to make net shape products so that we can reduce grinding, eliminate grinding in making engine valves. And what do? We do FEA simulation, and we understand what kind of tool materials are important and so on. One point is very important. For example, when we started this study, by the way, this is a $300,000 study over 3 years, but the money doesn't come from Eaton, the money comes from the Department of Energy. So this is one of those projects where the companies are very generous because they are spending someone else's money. Okay, they do that in Turkey, I guess, too. So that's one way of doing it. But one of the things we did was to one of the first things I asked my students is find out what are the best die materials for hot forging, what are the best coatings, and we prepared a state-of-the-art report that we could really give to Eaton as well as to other companies on die materials and coatings. So we are supposed to know as well as anybody what die materials and what coatings are best, what heat treatment we should use, what kind of coatings we should use, and so on. And of course, the main tool materials, Bühler, Güterholm, Dylo Steel, and so on. These are major steel manufacturers and major coatings, ballers, and so on. So we have to learn who's doing this, and we have to summarize this in a report. Incidentally, of course, I have an advantage. I have many friends. I called Professor Osakara. I said, I know in Japan they are using ceramic dies. What do you know about this? And he sent me some information. So we also got involved in using ceramic dies for extrusion. The process is very simple. I don't want to go into it. Looks very simple, but it's not so simple. Extrusion on the left side, and then after extrusion, coining on the right side. The process is automated. It's no secret. 20, 30 strokes a minute. Mechanical press, full automatic with robots. Lubrication is automatic, but there's a lot of issues. For example, it's the press bed parallel. What is the heat transfer from liquid lubricant to the dies? When you start at room temperature, the dies are cold, and then they heat up, just like Professor Bai showed when the lubrication, how material gets warm in sheet warming. The same thing happening here. So there's a lot of details. Elastic deflection of the tooling. As the dies get warmer, the shrink fit you have in the dies change. So there are a lot of details that one has to obviously look. So the in case of valves, we have to improve the quality, the tolerances, increase the tool life, and so on. All these things looks very mundane, but there are a lot of physical, chemical problems that have to be investigated. Second project with the same company, as part of the same funding, is bevel gears forging and spur gears forging. And those of you in forging business, you will appreciate that, of course. The bevel gears are, if they are done for automobiles, they are cold forged. That's technology that's already well known, developed in Japan and Germany. I'm sure it's being used in this country as well. But when you do large gears, large bevel gears for trucks, you cannot cold forge them. Because why? The presses are large, the tools are very expensive, and you have to do hot forging. When you do hot forging, things get a little bit tricky. The shrink fit of the dies is a little bit different because you have to take into account the stresses due to temperatures as well as the stresses due to shrink fitting and so on. And we use deform, and my graduate students do that, of course. And we try to, in this case, that was a problem. The dies were cracking after 1,000, 2,000 pieces. That's obviously very low. So we tried various things, and we came with the conclusion that to the company we said, you know, the best thing you got to do is change the radius at the end of the tooth, which is obvious, of course. And we kind of showed them that that has nothing to do with the function of the gear, and as a result, we were able to reduce the stresses in the tool about 40% by slightly increasing the radius. And I should also add that simulation doesn't give you answers. What simulation gives you, it proves or disproves what you think, and it gives you maybe approximate numbers. So you really have to think yourself what I'm going to do through simulation and what I think I'm going to achieve through simulation. Since we're talking about lubrication, let me give you an example. Another project we are doing with Honda. My approach is a little bit different. I am very practical and very simple, as simple as I can. The problem is this. Honda has several plants in North America. They said to us, each plant is using a different lubricant, and we don't know why. Everybody says their lubricant is best, and then there are other lubricant suppliers tell us, use this lubricant. How in the heck are we going to find out which lubricant is better? Okay, we said, we know how to do this, because I learned a lot from Professor Bai in the past, and I learned a lot from Professor Merklein in Erlangen, and I learned a lot from BMW, how they evaluate lubricants, and we devised our own technique, which I believe which is very practical. So one of the things we do, by the way, is in all our studies with sheet metal forming, we use our bulge test, because we have to know for FEM simulation the properties of the materials. By the way, all this information, not the confidential part, but the open information is available. So if you want to have something, send me an email. My email address is on the website. I send you the publication, or some of the slides are also on the website. What you can see here is, if I know how to operate this thing here, I guess maybe I do, yes. What you see here is the sheet metal. This is called a lock bead. I hold the sheet metal here so it doesn't move. I have a viscous material here, or I could also have oil, doesn't matter. And this is my tool in hydraulic press. I have a cushion. My punch is stationary. And when I push the upper die down, then this whole assembly moves down, and this liquid here is pressurized, and I push this sheet, make a bulge, and as you see, I don't have a gome system. The gome system, not that I don't know about it, but it costs how much? $50,000, $60,000? And I don't have that kind of money, more. I don't have that kind of money. So what I do is very simple. This is a $700 laser sensor, and this is a box here. When this is moved, the laser senses the height of the bulge. At the same time, I measure the pressure. From the pressure and the bulge height, inversely, I can determine the flow stress diagram of the material. By the way, I don't put K and N values. I don't use any equations. I use the actual data that I obtained after massaging through FEM. I use it as input to the FEM program. So we try to avoid extrapolation as much as possible, because all the people who do FEM simulation, unfortunately, they use a tensile test. When you use a tensile test, tensile material next, that means you have strains at small strains. You have stress at small strains. And you fit the K and N value. As soon as you fit the K and N value, then you don't know what the hell you're doing. Just like Professor Rolls showed, the extrapolation can be anywhere, and when you put that in the FEM program can take you somewhere you don't know where. So therefore, try to avoid extrapolation. Now, in this, coming back to lubrication, in this job, we had to, as I said, I learned a lot from Professor Bai because he's really the world's expert in lubrication, also from other people. And I want to design a very practical test. Now, if you were going to test 20, 30 lubricants, it's very difficult to have an extensive test procedure. So what we did is, we use a strip test. We draw the strip always to the same length because we have stoppers on our machine. We know the press comes always to the same depth, the ram. And we then measure the length of this strip because if this strip is longer, the longer the strip is, that means I must have stretched the strip. That means I must have thinned the strip. Therefore, the lubrication is bad. In this, this is the inserts we use. We can use different dye materials, different dye coatings, etc. to investigate the lubrication. And then this is our dye plate that goes in the tooling that we have. And once we select from 20, 30 lubricants, 4 or 5, then we test them in a dip draw test, as you see here. In dip draw test, again, same principle. As the edge of the blank draws in, the more it draws in, the better it is for a given blank holder pressure. I can test the lubricants at different blank holder pressures, and I can determine how good they perform in terms of lubricity. I must add, of course, the qualifications of a lubricant is not only coefficient of friction. It is corrosion. It is, can I remove it? What about when I want to paint the part? I am sure that people in the sheet metal forming business know all these details, but lubricity, of course, is very important. And this is our tool setup. It's very simple, by the way. If you guys want to use it in this metal forming center, it is available. We have a load cell here to measure the force. And here's our punch. And this is the blank holder, the die, and so on and so on. So all these details are available in published, non-proprietary papers. One more case study. Tyco Electronics. Maybe you know, they make a lot of electronic parts. And it's, again, world-class, worldwide company. This time they came to us. It was very strange. They had read some papers in Stamping Journal, etc. And they said, we would like to work with you. And they do high-speed blanking. High-speed meaning now 2,000 strokes a minute. Blanking very microform parts. Usually blanking, but also some forming. And what they would like to do is understand the whole process better, the physics, the dynamics of the machine, because these are carbide tools, tool life, the precision of the tools, the tool wear, what is affecting tool wear, etc., etc. And I said to them, okay, but you got to pay for it. I can have one of my PhD students working with you, and we send the PhD students for 3 months to the company in summer to learn more what's happening in their laboratory. They agreed. They are sponsoring now the PhD students, and everybody's happy. She's happy, by the way. She happens to be a lady from India, and we are very happy about this work. So that is continuing. So the objectives are: we can simulate blanking process. We can try to determine how the clearance, the punch radius, etc. affect the concentricity of the punch, affect the quality and the material of the blank, and so on. So there are many issues here because you're doing everything in a high speed. The material properties are not so easy to obtain. So the simulation is relatively easy, but the material data is not so easy. And of course you have to have very tight mesh around here, because you have very high strains up to 3, 4, not 4 maybe, but up to 2 to 3. So, and the issue is, can we predict also the tool wear? You don't have to predict the exact tool wear. You want to know what factors affect tool wear most. Is that the speed? Is that the sharpness of the tool and the material properties and so on? And other examples. This is very interesting. Everybody in the world is interested in a process called hot stamping. everybody in the world. Volkswagen, Passat, Volvo, I guess most cars, I'm sure Mercedes has it, they have hot stamp parts. What are hot stamp parts? I'm going to describe it in a minute. It is basically you heat a boron manganese steel developed by Arcelor to about 850 degrees centigrade, and you have to chill it, cool it, quench it in a die about, I believe, in faster than 29, 30 degrees centigrade per second. If you can do that, you transfer the austenite to martensite and you obtain about 1500 megapascal strength. The question is, the dyes are very expensive. Somebody was telling me they are talking about $600,000, $700,000. So how do you design the tooling? And I am delighted that this work is being done also in Turkey. And we are trying to simulate this process. And the process is this. You have two variations, indirect and direct, but the main thing is that you have to, you take the steel, manganese boron steel at room temperature. At that point there is no problem. You blank it, you heat it, and then with the robot very quickly transfer to a press, usually a hydraulic press. Schuler and APNT are the main press manufacturers, but others build presses too. And then you bring the press down. The closing takes about maybe 1-2 seconds, but then you have to hold it about 20 seconds until you cool the material, and then you hopefully obtain martensite and very hard material. The question is many issues. One, nobody knows what the heat transfer factor is under pressure. Number two, we found this out, of course, when you form the material, there is thermomechanical simulation you have to do because there is heat transfer at the same time while you're forming the sheet. And while you're forming the sheet becomes thinner, certain locations. When it becomes thinner, it may not touch the top and bottom die. And 1/10 of a millimeter makes a lot of difference in heat transfer. So all of a sudden, if you don't do the dies right, then you may have a part that doesn't have the hardness all over the place as desired. And we started with simulation form literature. That's what we do first, because that's the easiest way to do. Here we are also trying to determine what are the cooling channels, what is the best optimum way of designing the cooling channels, what should be the diameter, and so on. By the way, one of the students from University of Munich, from Professor Hoffmann worked with me, and I was very lucky that I have so many friends in Germany. I collected a lot of data on hot stamping from my friends. This is data not confidential. They developed under the Sonderforschungs program in Munich, Dortmund, and Erlangen, and they were wonderful. They sent me information, Professor Takaya, Professor McLean, Professor Hoffmann, and we collected all this data. This is very important. Again, students can do that right away. And when somebody comes to me now, I probably have the world's most collected information about hot stamping, because we spent about 1.5 years putting that thing together. As I said, we are working with a company called POSCO. As you may know, POSCO is a Korean steel company, very progressive company. And we work with two other companies, one Imra, Japan, and Verbam in Canada, and I hope that we will be working also with a company in Turkey. So, as I said, it's an extremely, what did I do here? Sorry. I think while talking, I made a mess here, okay. Okay, let me continue here. So, hot stamping simulation is a very big issue with us. And I see I show you some preliminary examples. So far, we seem to be on the right track, and our simulations show that we are okay. But here's another case study I show you. This company is in Belgium. They called me up from Belgium. They said, we saw that you do simulation, etc., etc. We have some problems. What is the problem? You want to assemble aluminum parts on a tube, and because we are going to make heat exchangers. And that takes a lot of experimentation. We don't know the size of the hole, we don't know the size of the flange. Can you simulate this? We said, sure. We wrote a proposal, and they agreed. And incidentally, when we write a proposal to a company, we make them in phases. The first phase is always very small, a couple of $1,000. And the reason is, the risk is small. When I tell a company, you know, look, if phase one doesn't work, you can cut it off. Your loss is $3,000, $5,000. You don't have to spend another $50,000 until you know what we are doing. So this is very quickly the example. Here is the sheet metal. Make a hole. We make the flange here, and then we have to assemble this to a tube. And there are many of them assembled together. And then there was another part of this project where we had to hydrostatically expand the tube so that this was an assembly process instead of assembling it by welding or by other means. We basically assembled it with friction. Let me pass. This is a Honda study. And we are doing a study in hydroforming. Let me skip that too. I think I'm running out of time. But let me just show you another example. This is very, very simple one. V-die bending and spring rack in advanced high-strength steels. We are again working with a company that builds press brakes, Upcon Presse, and they have already in their controller spring back calculations for regular steels, but they don't have it for advanced high-strength steels with the dual-phase alloys, DP600, DP780, and so on. So we did some experiments. Incidentally, the way I do it sometimes is I don't have all this equipment in my laboratory. So what I do is I send my students to the company to make an arrangement. It's sometimes complicated, but it's not that complicated. And the advantage is the students go to the company, see the equipment, and they do the test there in 1 or 2 days. It's much cheaper to buy a press and use it for a project, and then you don't use it. So the problem in press bending is when you experiment, it looks very simple, but measuring the angle under load after unloading is easy, because then you can take the part out and measure it on the CMM or photographically or whatever. And we are able to estimate by FEM the spring back in function of the punch strong. This is V-die bending, but FEM is not useful for the companies because they cannot buy a license and put in a controller. So we have also a more analytical program that we developed, and we are working with them to implement it. And the students love it because they have a program, they wrote it, we checked it, it works. Now it's being implemented in industry, and they feel very proud of this, and it's good for them when they go later to a job. My last 2 slides, this is a very interesting project. You might say it's micro forming. Please look at the dimensions. You will see that we are talking about 4 10,000ths. This is inches, by the way. And no, I believe, yeah, they are inches. These are inches. The dimensions, you see 6,000 of an inch. And what we are trying to do by cold forging from a wire, we are trying to make a part like this, which will be used for eye surgery. The doctors do not use an eye surgery tool. After they use it once, they throw it away. They don't wash it and use it again. So they sell zillions of this thing, and they used to make them by forming and grinding, and we were able to simulate this for them. This is the simulation. As you see, this is interesting. The finished part has a 0.01 inch flash, and this flash is removed by chemical etching. Now, we work on this project with a Becton and Dickinson medical company, and then a tool company that makes carbide tools. We don't know how to make carbide tools, but we know how to design carbide tools. So we taught the tool maker how to design, how to calculate the stresses, how to reduce the stresses, what type of carbide to select, and so on. It was amazing when you talk with a guy who has 30 years of tool experience. He says to me, "Boy, I really learned something from you. I never thought carbide would elastically deform so much." But we could show him that because of the E-modules, there was an elastic deflection, and we had to calculate the elastic deflection in tooling to obtain the exact dimensions of the knife, because machining is very expensive, grinding is very expensive, and we had to reduce costs. So I think I stop here. I could go on and on. I have other examples, but the point I want to make is that if first I have been through this kind of establishing a center at least 3 times. When I joined Battelle, there was one person besides me in metal forming. I built a group to 25 people, but the only way I could build is what? Bring a job, hire somebody. Bring a job, hire somebody. The university, we were luckier, we wrote a proposal to the government, and then we got some money, and then from industry and so on. Now this is the 3rd one. So there is the importance of trust you establish in a university with a company is extremely important. And once people start showing the reputation and they say, hey, wait a minute, we can trust this guy, he means what he says, or he says he cannot do it, then you are doing okay. So I hope that helps to people in the metal forming centers. Maybe, maybe not, I don't know. So, thank you very much.
I have to thank Professor Altan. He showed us he's not only great scientist, also he's great teacher. In the late afternoon, everybody listened to him carefully. Is there any question and comment?
Either I was so clear or what I said didn't mean anything.
No.
You are so clear.
Yeah, thank you very much for all the comments. Related to the bending example, V-bending you had, we do similar work, and what we found was that the scatter in the material is so big that we have to measure online the material properties. Do you do something similar in your work?
Yes. We go initially with the material properties, but especially with the advanced high-strength steel, we definitely have to go once, come back once again. You're absolutely right. We do the same thing what you do. Yes.
Can we go to the slide 12?
Slide 12. Yeah, that's okay. Thank you. I go up there. You caught me for something I don't know about.
It's a cup deep drawing.
Cup deep drawing. Yes. Slide 12. Yes.
Yeah.
By the way, we always number our slides, so it's easier to identify.
Yeah, it is.
Yes.
So my question is, you have a comparison flange diameter with the friction.
Yes.
So are you using the same sheet quality, because there is also
Yes.
effect of
Absolutely.
anisotropy and so on.
When these blanks are cut from the same lot of material. Absolutely. Otherwise, you're right. And I use the same blank over force. And for each test, I make 5 or 7 samples. And when I give the data, I give the error bar. Because that's also important.
So then you have a relative comparison between which lubricant is the best and so on.
Sure. Also, through FEM, I can calculate this for a given coefficient of friction, so that means inversely I can also determine the coefficient of friction.
Super. Thank you very much for a nice and cheap idea. Thanks.
My pleasure. I got it by the way from BMW.
Yeah.
Is there any other questions? Or comment? No comment, no question. But I want to make a remark among what Professor told us. One word, he said trust. If there is trust, I am sure contact, collaboration, connection, and everything among two human beings would be possible. Thank you very much.
Thank you. I'm all done. Let's get rid of this. I don't know how to do this.
The second paper will be presented by Mr. Erkan Polat from Tofaş Automotive Company. His speech title is challenges for metal forming research in the area of automotive and rail. Whatever it is.
Thank you, Mr. Chairman, and thank you, organizing committee, for inviting me here. And I wish very good success to Metal Forming Excellence Center. I'm going to present you metal forming challenges in coach group, automotive and house appliances industry. And it is already late afternoon, and it won't be very easy for me to take your attentions as much as Professor Altman's grabbing speech, but I'll try to make my best. I have also some interesting material for you. First of all, let me very briefly introduce Koç Group company. Koç Group is making around $40 billion revenues consolidated for 2007. And in total, we have 85,000 employees. Almost 50% of the employees are from automotive and consumer durables industry. And we are number one company in Turkey, and also as you can see the ranking here, 2006 values. I don't know the 2009 figures, but we were in the first 200 companies in the world, Fortune 500. Main business sectors are energy, automotive, consumer durables, and finance. For automotive sector, Koç Group has international allies with Ford Motor Company and Fiat Auto. Tofaş is a joint venture with Fiat Auto, and I'm working in that company. So if you go to presentation, I'll give you some examples what we are doing in Tofaş, in Ford, Otosan, also in Arşivi. Arşivi producing house appliance durables. So maybe everyone also aware of it, but longest tool development process in car development is the tooling of the sheet metal stamping dies. And it's around 25, even 30% of the development cost is tooling cost. And also, we are not buying the cars only for the fuel consumptions, but mainly we are buying cars for the appearance. So the quality starts with the sheet metal stamping. If you cannot stamp a good quality sheet metal parts, then by rework you cannot reach a perfect surface quality. So we must start with a perfect surface quality comes out of stamping dies. And we are talking about stamping dies as big as 2.5 meters by 5 meters. And at least 5 operations or 4 operations to form a body side. And when the part, sheet metal part, the blank part, comes into draw die, and we get the part and at the end of the line, and each time we are stamping with 2,000 ton or 1,000 ton, and even a small drop of piece into the die, you will see onto the piece. So the process is extremely delicate. So I'll present the activities we are doing in Tofaş. We have a team of die designers, 14 engineers. We are developing something 33,000 hour engineering capacity only for die designs. In this section we are doing stampability analysis, prototype designs, process design, and of course 2D and 3D designs. So the main issues are starting with stampability analysis here, and process design, and project review, and which is very important because we are bringing into all our know-how coming from last projects, and then start die design. Stampability, what we mean by stampability, we are working together with a product developer. By simulating the process and also by use of our experience, we are changing some part of the products if we can make the product developer accept it, because life is not easy and mainly it's a compromise between the process and the product. If only they would let us, we would design maybe very simple shapes, but we cannot sell those cars. Maybe very easy to stamp, but we cannot sell the car. So this is the first process, working with product development, and while we are developing our stamping process, working together with product development. So it's a simultaneous process. Meanwhile, we start process design. In the process design, we define how many operations to be applied, starting from blanking, drawing, trimming, and subsequent forming operations. Then we are simulating all operations, full cycle explanations. And up to some years ago, we were only simulating drawing operations. And we can now fairly good predict the drawing operation. And we don't need any more iterations for the draw operations. Even for such a complicated part like body side, we can stamp the part at the first trial. Of course, after making first spotting. But drawing is not sufficient. Because after drawing operation, after trimming, after forming operations, the geometry you get is not the nominal geometry, because you have deviations and also surface defects, and we don't want it. And traditionally, what industry was doing, and still we are doing, but every day we are reducing it, working under press, which is called tryout, by an experienced craftsmanship of a die maker, working under press in order to eliminate all the surface defects and also correct some springback effects, which is a very long process, time consuming and very costly. And also this process, I'm talking about the tryout process, is after when you complete the die set. And you have, at the same time, you're starting to produce first series of the car. Of course, we don't sell those cars. This is process verification cars and pre-serial cars. But the process getting longer and longer. So if we can completely simulate the process, and we are not succeeded in totally predicting surface defect and springback effect, we can make the tryout virtually. I mean, on the computer we can make the tryout process. So it can be made simultaneously. So we don't have to complete the dice and to make the trials. So after this, also an important phase to be done, not only for the geometry and the surface defects, but those dice should produce at least 500 pieces per hour, and even more, every day getting more and more, so that even this scrap evacuation can be a problem, or other quality issues. So apart from the simulation results, we have to bring into all the experiences that we have from the similar projects. So we are accumulating this know-how. Also, we are writing this know-how to a know-how book, so that we can make use of it for the next projects. So even though each cars are different as a styling, but there are many common part of the parts. Another issue is prototyping. To make the crash test, also other tests we need some early series of the car body in order to produce, because nowadays more and more virtual crash tests and virtual tests, but still we need to make physical tests. Therefore, we need to make prototype tools, and these prototype tools should produce at least hundreds or sometimes 200 pieces. And those tools has to be very cheap, because you don't want to spend a lot of money, and has to be very fast. Within 6 months, 6 week time or 8 week times, we have to complete all toolings of a car. What we do, we have applied patent for this process. We use polyroll materials, but polyroll materials is very expensive, and you can make a mass casting, and you can high-speed mill it, and you can obtain the same results. But here the idea is we use the process data, I mean CAD data, developed for the definitive tooling. And we don't need to redevelop a surface for prototyping. We use the same data. And by use of the CAD data of the drawing operation, we generate this design of this carcass structure. Of course, this seems to be very tedious job. To develop this, we have developed a software to reduce the time to design the die. So in order to design this one die set for a draw die, we need only 2-3 days. Everything was done automatically. Then in order to make this steel structure, we have some supplier in Bursa region, and they have laser plasma cutting machine. We send them the data within 7 calendar day, not the work day. They supply us cut and welded structure. So we need to cover to the welded structure the polyroll material, plastic material. So the plastic material thickness is maximum 20 millimeters thickness, and we leave 5 millimeters stock for machining. So at that we reduce the time. We also reduce the material consumption, plastic material consumptions. Another advantages from this technique, of course, you can use for the thin materials. I mean, you can use this for up to 1 millimeter thickness, even maybe more. But for the inner parts, like 2 millimeters, 2.5 millimeters cross members and so on, you cannot use. For steel material, this has an enormous advantages as a cost and speed, but also the advantages under press force. The spotting is easily done because this structure deflects and copy each other, so you don't have to spend time for spotting. That's another advantages versus use of steel material in prototype tooling. Then we designed the dies. We also designed transfer dies. We also need to check the collision. We have a kinematic analysis, because the dies are not a simple 3-piece dies. Only draw operation is 3-piece. The rest of the operations are always with cam operations. Therefore many pieces moving in the dies. Therefore, in the design phase, we may have made some mistakes. Therefore, we make the collision check by kinematic analysis, so that we don't have to correct in the tool shop. We also have to optimize the pneumatic component selection under press cycle. I'm talking about large size presses, so we are making 20 intermittent strokes. So it means that we have 3 minutes, 3 seconds. But within 3 seconds, the cycle time of the cam operation is something around 600 milliseconds. So within 600 milliseconds, all the movements have to be completed. I'm talking about some cam units is heavy as 2 tons. So if we choose big size pneumatic components, maybe we are spending too much time for the pressure up. If we choose very small one, we are losing time for the ramp up and the ramp down. Therefore, we use also some pneumatic optimization program. This is some improvements on the design, because if you use a general purpose modeler CAD program, you spend too much time for design, and also you lose standardization. Therefore, we have developed some macro programs and some programs in order to shorten die design lead time, also increase the standardization. That also helped us a lot. Then we are coming to the reverse engineering. So, as I said at the beginning, we need to make in the future perfect full cycle simulation, and we have to rely on material, and the material model is perfect, and the solver is running perfectly, and we may solve the problem totally, and we may not need to make additional iterations. But whole industry right now, after stamping the first piece, making some corrective actions, which is called tryout. So even tryout, traditionally done under press by use of the experience of the die maker. But nowadays, what we are doing, after stamping the first piece, scanning the piece, and identifying the area, the deviations, then by reverse engineering, creating the surface and modifying the surface, and coming back to the draw operation, remachining, and if necessary, machining the subsequent operations like trimming operations, forming operations, and then go to the press again to obtain the perfect geometry. So nowadays, we, by use of full cycle simulations, we have already reduced some iterations. So the technology promising. Also another issue for die design, for the body side, 2.5 meters by 5 meters size of a die. So under 2,000 ton press pressure, the structure itself deflects, and there is no perfect stiff die for it. Even you make a full solid casting, your press table will deflect. So we know this, and we are not trying to avoid, or we are not trying to increase the stiffness of the die, but during the die design we are trying to optimize the mass so that we can reduce the weight of the die, but we can keep the deflection more or less at the same level. But afterwards, if you know how much it deflects, we can compensate the deflection. Nowadays, for the female part, we are applying some corrective modification. We are modifying the surface, of course keeping the punch in the nominal CAD data, and we are reducing the spotting time, which is also an important cost component. In order to make this study, we have also measured real deflection under presses and make the calculation by use of abacus. We worked with University, and the results was the physical deflection and the calculation was correlating to each other. And now we are using only Katya solver, which is sufficient enough to calculate the deflection. So during the design phase we are using, this is not only for the research but for the daily design activities we are making the analysis of the deflection. So in TOFAŞ we are, our main issues for the research, precise simulations, of course, as I said, of course more efficient die machining strategies and conditions, and high strength steel forming, simulation of the process, and hot stamping is another issue. But at the moment we are not stamping, hot stamping, but Fiat is using some hot stamped parts, and also more efficient soft tooling. These are TOFAŞ's main R&D projects. In also Ford Otosan, this is Ford Otosan die design and manufacturing department. They have as much as 300,000 hour capacity, more or less the same capacity that TOFAŞ die production plant. So this is an example from Ford Otosan. So I should tell another things that TOFAŞ and Ford Otosan is not only producing dies for their own use, but as a profit center, we are using dies for other OEMs. This is a case from Ford Otosan. To produce aluminum outer panel, they have made the similar studies. So this is the part, aluminum roof. So they have made the virtual surface development and stamping simulation. After stamping simulation, they have made the virtual dimensional measurements. So they, before manufacturing the die, they have virtually produced the part and make the dimensional checks. So the objective is to be in geometry 90% and the virtual surface defect control. And of course objective is zero visual defects. And then if everything is okay, we go to the die production. And this is another example for the lead time reduction. On this example, by optimizing the process schedule, they have reduced the lead time up to 8 weeks. This important earning. So in a year they have saved 1.4 million Turkish lira. So this is another example from the research project for the draw bead. And I want to show you some examples also from Arşivi. But the challenges is more or less the same, even though the parts are completely different. Of course, more accurate simulation, faster die tryout, and to make a faster die tryout, we need to make virtual process validation, blank size optimization, and optimum die stages, stainless steel forming simulation, surface engineering, and less duplication. So this is their organization. They are relatively smaller as a die shop. So these are the examples that Arçelik is making: progressive dies, transfer dies, dies for stainless steels, lamination dies, plastic injection molds, rubber molds, thermoforming, and automation tools. So as a first step, Arçelik is also doing the stampability analysis. Process parameters are determined. This is optimization of the part design, so that some product changes here to be able to stamp without any split. They make some engineering changes. So as you can imagine, they in also housing appliances we use steel, and we have spring back problem here. So the spring back is calculated and compensated. So prototype tooling, and these are the examples from the tool sets used in Arşivi. So for the tandem press line and transfer press lines, also progressive tool sets. Some examples from reverse engineering. The main R&D projects are semi-automated part design, surface treatment to increase the lifetime of the dies, elimination of the operations by combination of the forming operations, trimming operations, elimination of the operation and elimination of the scrap means that increase of the use of the utilization of the sheet metal, optimization of the part and tool design, and also use of different stainless steel to reduce the cost. These are the main R&D projects of Arşivi. So thank you for your attention.
We are going ahead of time. We have one more talk, the last one, but I don't think it will be this one, because the last talk, which will be given by Professor Tekkaya, is founder of Excellence Center. But let's just a minute.
Okay.
Just a minute. I was in a hurry. Before going to Tekkaya's talk, there might be questions and comments. Mr. Erkan Polat's paper is open for discussion. Is there any question? Okay.
Yeah, thank you. I have a general question. That's very impressive what is done in the two companies, in the three companies. As you know, Turkey is the champion in the world in increasing the CO2 emission. We were absolutely number one in the world. What are you doing to reduce that in your company?
Well, it's a very good question, because I have an answer at least from the Tofaş side. Before launching the last product, which is a new Doblo, as a development, we have changed all the standards of the Fiat Auto was using in order to reduce the material utilization, increase the material utilization. As you know, in this sheet metal stamping, we have an inevitable scrap. We have a binder and we have addendum. So we need to reduce this. So in order to reduce this, we have initiated a work. And we have saved 32 kilograms of sheet material per car. What we have done, we have reduced the size of the draw beads, for instance. Because if you have a draw bead, 16 millimeters, something like this, all around the die, so if you can reduce it to 12, so we can earn 4 millimeters from this side, 4 millimeters from this side, 4 millimeters from other side. So the draw beads, if we can make the draw beads closer to the die opening, we can also save from that. And traditionally the addendum surface has 80 degrees or 85 degree angle. If we can make it steeper, we can save. But in the past, as we don't have such simulation tools, this was a standard. So better simulating process, we take more risks to reduce the material. So at the end, 32 kilograms of material, if we are going to produce this car, 1 million in total, so it's a a lot of saving. So for 1 kilogram of sheet metal, we are saving 2 kilograms of CO2 emission. So this was done by die development, but also for product development. Our R&D department worked on reducing the weight of the cars and also engine development, but I don't know those areas. But I can talk about the die development area. This was...
Time is pressing us. We may get one more question. If there is no question, or if there will be any question, I think during visit of Excellence Center, I think everybody may have contact with the speaker. Now I invite Professor Tekaya. Professor Tekaya's topic will be Challenges for Metal Forming Research. Sorry, a Center of Excellence for Metal Forming, Motivation and Establishment.
So, thank you very much, Professor Uçuşuk, for this introduction. So, it's always difficult to be the last speaker, but I think I will talk about a nice topic, but not going too much into the depth of theoretical issues and technological issues. So I hope you will enjoy the last talk and just let it dim out the mood you have. First of all, I would like to thank all the speakers, all the international board members, all the administrative board members who are here and supporting us in this metal forming center endeavor. And I would like now to give you a brief overview of the motivation and establishment behind this center. So, just starting with the slides already partly mentioned by Professor Felice, megatrends. If you look to some of our students, I had one student, a very smart lady, and I asked her to make PhD with me, and she said, "Oh, I do not want to do research on the grandfather's topic," so she went away and is working now on nanotechnology, which is one of these topics, which is of course in mobility, energy, and also in the field of communication and health and security, of course. But in order to make those megatrends, which are very popular and which we know very well, we have to get them true, we have to realize them, and that can be only done by real life manufacturing. And this manufacturing is also the topic of the famous report of the European Union, which is the report Manufacture, which tells in a conclusion that we need a society which is knowledge-based manufacturing, and this society which has the knowledge-based manufacturing will be able to realize all those megatrends, all those dreams most probably young people have, and without that we cannot even realize those topics. So, and that was the reason for us to look to production, manufacturing. As you know, manufacturing is one of the locomotives of the export and the economy of Turkey. And this very highly expanding branch and strength of Turkey has some challenges and some weaknesses. Now, one important point is related to the challenges coming from three different type of clusters of countries. One cluster is definitely China and India. Those countries are booming and their export is booming, and currently they are trying to satisfy their own domestic demands, but if they are satisfied they will look to other markets, and then we have a big problem in Turkey. The second cluster, which is coming, which is challenging Turkey, the industry of Turkey, are the geographically nearby countries like Iran, the Turkish republics, Azerbaijan, Turkmenistan, and so on, and Lebanon, and nowadays also Iraq. Iraq is pushing up as well. And the third cluster is, of course, the well-developed countries, which have high technology, high efficiency, and those three different group of countries are challenging the Turkish industry, and we have to cope with them in a standard technical way, of course. But in doing that, our industry, especially our forming industry, has some weaknesses, and one weakness, maybe it's not correct to call it as a weakness, but one property is that most of the Turkish metal forming industry is small and medium size. That means they have relatively restricted resources and cannot invest in research and development like Daimler, like Koç, and other big companies. Now, the Turkish forming industry is not organized. Taylan Altan said, as he was in Turkey, he organized the forging companies to build a group, and after 1 year, 2 years, this group disappeared. So organization, networking like in Europe, like in Japan, is not present in Turkey. Research and development is still something which the Turkish industry has to get used to and has to learn. So all the concepts in Turkey are shifted. If we are speaking about engineering, we mean technical issues. If we speak about research, we mean engineering. If we speak about science, we mean research and development. And if we speak about more, then we hopefully mean science as well. But that's a big problem. The other problem is, at the side of the universities, the Turkish universities have a lot of professors, very good professors, coming from the best universities from the world, but only very few of them, especially in mechanical engineering, maybe less than 5%, have ever worked in the industry. And that's a big problem. If you look to Germany, for instance, I would say like 5% of the professors were at least 5 years in industry. And that's a big advantage. And you should be aware of that. We got our technology always from Europe, but manufacturing research in Europe is now in a downtrend. It's reducing. So we have to stay on our own legs in the future. Coming from that, we need in Turkey, for the next 20 years, a specialized research and development center. That's the result we found here, to ensure competitive power, to ensure that we can produce new products and that we can be technology leaders in some field. And those brought us to the aims of the Center of Excellence for Metal Forming. We would like to develop, we would like to have a center which is producing manufacturing technology which is knowledge-based, which can help to produce products with high added value, not only cheap products. Turkey has an export of $130 billion this year, and the import is more than that. So that means the added value which we have in our products is not high. So we should look for new materials. We heard today about lightweight structures, aluminum, composites, mixed materials. We should have an increased productivity. Micro forming is one issue. We heard today 2 very nice talks which were touching that topic. And we should push up innovation for product development. And after all that, we would like to be the best center in this field in Turkey, but not only in Turkey, but in certain fields also in Europe, maybe internationally. And with that in mind, we found the center which has one speciality which is quite unique in Turkey, at least, which I will mention in a minute. First of all, we have an international advisory board. I will introduce the international advisory board in a minute. Those people are the gurus in their countries, and they should guide this center and tell us if we do something which is not correct. And I must say, yesterday we had a meeting and this center did its job completely satisfactorily. Give very good comments and very, very good suggestions how to proceed. Then we have the administrative board, and this board is very special. This center is founded at a university. Despite of that, the major decision board, which is the administrative board, consists of 2/3 industrial members. So we have industrial members corresponding to 66% of the board, which determine what this board has to do, what kind of mission this board has to buy, how it has to work, and so on. And then we have an executive council, which is doing the everyday business. And the working strategy is like that every work is done within a project, where the project team consists of a co-worker from the center, which is a research assistant, usually, and a supervisor, usually a professor, or an associate professor, assistant professor, and a member from a company which is working in that team together. Professor Osakada made an excellent suggestion today. He said we should improve that picture by having also a member assigned from the International Advisory Board to take a look to the progress of the work. I think that's a very good suggestion, and we will follow that in the very near future, definitely. So, our administrative board consists of the very outstanding companies of Turkey, Oras Bearings. Feridunbey is among us as the chief of the production. Turkish Aerospace, TAI, which is represented with several co-workers here. I'm very happy that they are here. Asash Aluminum, which is the biggest company in Turkey producing aluminum with extrusion and rolling. Coşkunöz Metal Forming from Bursa, which is the #1 tool maker in Turkey and press maker as well. Kanca Forging, who is one of the most innovative forging company. Norm Fasteners from Izmir, the biggest fastener company in Turkey. Tofaş, we just had a presentation from Tofaş and Koç in general. Then we have 2 software vendors, Figes, presented by Tarık Öğüt here, who brought the finite element methodology commercially to Turkey, and Bias, who brought the nonlinear aspects of the finite element method to Turkey. Aydın Kuntay should be around here. And then we have 4 universities, of course Atılım as the host of this center is presented with 3 members in this group. The Istanbul Technical University, the Boğaziçi University, and the Middle East Technical University is presented here as well. Sabri Altuntaş, Hakan Gür, and Haydar Livatyalı as 3 colleagues. Then we have our International Advisory Board, which is spread over the whole widely industrialized countries, in which 3 of them are from the industry. Professor Roll had today a very nice presentation. Professor Alankuş was presented by Hakan Bey today, and Dr. Hensel, who was unfortunately hindered to come in the last minute, so he could not join us today. Then we have our board members from the academic world, and I just want to ask maybe the members to, no, I don't think I have to ask them to stand up, because you know they give the presentation, sorry, we don't need that. Niels Bai, Frank Follaston, Kozo Osakada, Karl Kusman, Jean Joly, yeah, instead of Professor Mikari, Professor Felice came, and Thailand Altan, Doyle Yang, and Dr. Julian Allwood could not attend this meeting from Cambridge because he had another meeting. But this group is guiding us and motivating us to do the correct thing. I'm very thankful to all of them. Yes, how have we established the center? The Turkish State Planning Department or organization has given us the biggest support after a proposal, DPT, and I'm very thankful for that. The Atılım University itself gave us more than 40% of the support, and the companies which were in the administrative board have supported this establishment as well, with support of material, with support of human time, and so on. So totally we have a budget of roughly $8 million US, and the project has started in January 2008. We had a very nice founding meeting that was in February 2008, and all the decisions have been forged in that meeting, and then afterwards we just tried to modify them and revise them with the different meetings. Okay, the center is at Atılım, and this is the building where we will go after this meeting to have a visit if you would like to do that. And the main building consists of 3 parts. One part is the building where the offices are and the conference rooms are. The main hall is for the equipment, heavy equipment, in which we have a small part, a separate room, where we have the delicate equipment for measuring techniques, and we have the micro equipment and computational equipment in the third building over there, which is an extension, and that contains the SEM, the electron microscope, and so on. And that's the final view of the building. Okay, I do not want to go through the chronology. The important thing is we started with the idea in July 2006, and the project is completed in December 2010. DPT, the funding institute, told me that this is one of the very few projects which has been completed before its time. So I'm very happy that we had the opening ceremony already in April. Okay, the staff itself consists of various professors, which are in various fields like mechanical engineering, metal forming, in material characterization, in numerical methods, and I do not want to go through all that. You have that in your notes. It's a very strong group consisting of a lot of people. We have also citation papers, although Professor Altan said that this is not important. As a Turkish professor, I suggest you don't believe that. It's very important if you would like to be promoted in Turkey, but if you want to go to the state, that's something different. But in Turkey, unfortunately, you need that, otherwise you don't get a professor. Yeah, then we have master and PhD theses. Some are completed, some are in work, and that's in fact our backbone of the whole research. We do all the research basically with our master students and our PhD students. The center's activities are divided into 4 basic groups. The first group is applied research. That's the heart of our research, of our center. We would like to do research for the industry. That's our basic mission. Then basic scientific research, that's more of academic interest. Technical services, those are the services we offer for the industry, like material characterization, like measuring techniques, and similar services. And of course we have education, and tomorrow you have 4 very nice workshops, very nice training workshops where you will have interesting topics like simulation and material characterization and code forging and so on. Okay, the center consists of basically 4 departments. In fact, one unified department, characterization, mechanical and microstructural, one metal forming technology part, and one metal forming simulation part. We saw today in all the presentations that simulation is extremely important, so I think this will be one of the important things. So I'm just giving you a very short overview about the equipment. This equipment is of course prerequisite to do any kind of basic research and applied research for the industry. We have a full set of optical measuring system. We have a testing equipment which can test material up to 1200 degrees Celsius. We have a Zwick-Ericsson test machine by which we can get FLDs, which are required for sheet metal forming, and we have the classical hardness machinery. We have one residual stress measuring system, which is very important. I think there are very few institutions in Turkey which have this ability. And of course we have a scanning electron microscope and the remaining issues here. The production technology part consists of the 400-ton Schuler press. I hope we will have soon a Coşkun Öz press as well in our lab, which is maybe even bigger than the 400-ton Schuler press, so that we can do also some work for the automotive industry. We have servo press. We had today the presentation of Professor Osakada about the importance of servo presses, and I think we are one of the first institutions in Turkey which can give you the opportunity to test this press, which has very nice features, very nice possibilities. Our press has a supplementary equipment which is a hydraulic ejector, so we can use it also in a two-stroke way for certain cases. And then we have a mechanical press, which is in fact Komatsu Mai press for doing cold forging. Then two Turkish presses, one CNC bending press and a shear press from Baikal, which we use. The machining side is very important because we would like to produce tools as well and specimens as well. To produce specimens we have especially wire-cut EDM, and for the tools, the grinding machinery and the turning machinery as a CNC center, as well as the milling center over there. And another important lab which has been brought by Professor Kaftanoğlu to the center is the CBN coating laboratory. The coating subject has been mentioned today also quite often in various talks. It's tremendously important to extend the tool life by this methodology. Forming simulation, we have almost all software available at the Institute with a parallel computing unit of 112 core processors. So if you need any computational power, you are sincerely invited to make use of that and of all our knowledge about this project. I'm not going to explain you all those projects which we have done already, although we are just opened in April. We have already completed several projects. Spring-back examination and deep drawing with Renault. We had experimental determination of formic limit diagrams with TAI, material characterization with Norm, the same, the tool design with SOM, and then with Dortmund, we had other work on determining the FLDs of certain materials, and with ORS, deep drawing work with SOM, cold forging of aluminum, and with Kanja, fracture and aluminum forging, and with some other companies, specific parts which we designed and developed at the center. So I hope that we can increase this, and I hope that our guests here, especially from industry, will be good partners of us. We would be very happy to collaborate with all of them, and I would like to invite you to visit our lab, and thank you for your attention in the last minute. Thank you very much for your patience.
I thank Professor Tekkaya not only for his presentation. Since 2006, to establish this institute by himself, by his colleagues, his friends, his students, I think this will be good and valuable institutions, and in near future many products will be coming. I hope, like Professor Tekkaya, Atılım University will have new staff, new faculty members, new graduate students, so that in Excellence Center and the other laboratories which I started noticing as of yesterday, we will be producing good works. I am sure Professor Thailand may also will like whatever will be done here. Now, since you are going to visit soon Excellence Center, but before going there, maybe you may have questions and comments while Professor in front of microphone. In fact, you will be able to contact with him, I think, over there also.
Yeah, definitely.
Is there anything you would tell?
So I think we can have the discussion also during the visit of the center, if there's not a burning question. Okay.
Okay, thank you very much.
Thank you.
Congratulations.
So, I wish you all a nice way back, a safe home journey, and I hope we will cooperate in the future. Say just the last words for closing the session. Thank you very much for all.